So this question, we're going to get introduced to the reaction quotient. The reaction quotient is calculated in the same way that you would calculate a Kc value. So the Kc expression is used to calculate Kc, but it's also used to calculate something called the reaction quotient. How can it be used to calculate something different? Well, when you're calculating a Kc, the concentrations that you have to put into the expression are the equilibrium concentrations. If you use any other concentrations, if you put the initial concentrations, or you put the concentrations halfway towards equilibrium, if you put any other set of conditions other than the equilibrium set, then what you're calculating is not the Kc. The Kc, you need to use equilibrium concentrations. So if we were to use any other concentrations, instead of calling it Kc, we call it the reaction quotient, and we call it with a symbol Q. So look at that balanced equation. Write the expression for Q in the space after part A. So the expression for Q, if you understood what I just said, it's the same as the expression for Kc. So it's going to be concentration of NaCl squared divided by the concentration of NO squared times the concentration of chlorine. Now we have a set of conditions in part A, the NO, the Cl2, and the NoCl. We know their concentrations. The question wants to know, is this set of concentrations at equilibrium? Is this an equilibrium set of conditions? If it's not, then we have to predict what direction will the reaction shift? What direction will the reaction head in order to reach equilibrium? Will the reaction go forwards, creating more NoCl and less NO and chlorine, or will it go backwards and create more NO and chlorine and less NoCl? So if it's at equilibrium, then there is no shift, right? At equilibrium, the rates of the forward and reverse reactions are equal. But if it's not at equilibrium, the reaction would either go forwards to reach equilibrium, or it would go backwards to reach equilibrium. And we have to predict that. Now we know Kc. The question told us Kc is 14.9. So can you tell what we're going to do to decide if the reaction is at equilibrium? We're just going to put these concentrations into the expression and calculate Q. If we're at equilibrium, Q will be equal to Kc, won't it? Yes, was there a question?
Yes. Could you re-explain what the reaction quotient is?
Let me finish the question, and as I do so, I will reiterate what the reaction quotient is, and if at the end of it you still don't understand, ask me at the end, okay?
Okay.
So we are calculating the reaction quotient using the same expression that we would use for Kc, but we're putting in these concentrations that may or may not be equilibrium concentrations. So the NoCl is 0.40 molarity squared. The NO is 0.50 molarity, and that has to be squared. And the chlorine is 0.25 molarity. So grab your calculator and get the value for Q. So I get 2.56, or I guess 2.6 if I have two significant digits. So there's my value of Q. So was this set of conditions at equilibrium?
No.
Why do we say no? Because Kc was 14.9 and Q is 2.6. So we can say here, since Q is not, actually let's not just say it's not equal. Actually, no, I will do that. I'll say since Q is not equal, put an equal sign with a slash through it. Since Q is not equal to Kc, we are not at equilibrium. Okay, so right there you see a very simple reason for calculating Q. You can tell whether or not a reaction system is at equilibrium. We got 2.6, Kc is 14.9, so no, this is not at equilibrium. But if that's all Q can do, then it's kind of lame, right? That's kind of weak. So yeah, it's not at equilibrium. But if it's not at equilibrium, is it going to shift in the forward direction to reach equilibrium? Or is it going to shift in the reverse direction to reach equilibrium? How do we decide that? Well, let's be a bit more specific.
Reverse.
We know that Q is not equal to K, but can we be even more specific? K was 14.9 and Q is 2.6. So Q is actually less Kc, isn't it?
Mhm.
So
Yes.
if we're going to reach equilibrium, we know Kc does not change, right? Kc is constant. But what will have to happen to Q if it's going to reach equilibrium?
It has to go backwards.
Well, I'm asking what has to happen to Q. Q right now is less than Kc. So will Q have to get bigger or will Q have to get smaller?
Bigger.
Q needs to get bigger, right? Because it's right now it's too small. It's less than Kc. So Q has to get bigger. Well, how can Q get bigger? Look at the expression for Q, okay?
More
Q
products.
is equal to products divided by reactants. How can you get that to give you a bigger answer?
Need more products.
You would need more products, right? A bigger numerator. And you'd need less reactants. You'd need a smaller denominator. So if you need more products and you need less reactants, what direction is the reaction going? Is it going forwards or backwards? If you're getting more products,
Forward.
it's going forwards, right? So when Q is less than Kc, we get a forward shift in equilibrium. The reaction will shift forwards to reach equilibrium. Now, I hope you understood the reasoning for that. Q needs to get bigger because Q is smaller than K. For Q to get bigger, we need a bigger numerator. So we need more NOCl. We need more product. To get more product, it'll shift forwards. Having said that, you don't need to explain that in detail all the time. You just need to memorize. When Q is less than K, forward shift. Okay? Try part B. Calculate Q. I'll be lazy, I won't rewrite the expression, it's the same expression, but put your numbers in. So the NOCl is 0.0200 squared over 0.0100 squared, the NO, times 0.269. What does this set of conditions give you for Q? 0.02 squared divided by 0.01 squared divided by 0.269. Do you get 14.9?
Yes.
Yeah.
So what does that mean? Are we at equilibrium?
Yes, sir.
Yes.
Yep.
Kc was 14.9. So we can say since Q is equal to Kc, we are at equilibrium. So what direction will the reaction now shift?
Nowhere.
Yeah, it's a trick question. You're at equilibrium, so it doesn't shift in one direction or the other, right? It's at equilibrium. The forward and reverse rates are equal. Okay, the last one. Can you guess what's going to happen here? Okay, let's calculate it. Q is going to equal 1.50 squared divided by 0.300 squared times 0.0500. I wonder what we're going to find. Did you get a really big answer? I got 500.
Yep. Yes, sir.
Okay, so the first situation back in part A, Q was not equal to K, and in fact Q was less than K. So that meant we were not at equilibrium and there was a forward shift. What we have here is Q is bigger than KC, right? You don't have to say it's not equal, we can just say it's bigger. Can you reason out what has to happen then? Like logically, it's obvious what will happen, but can you just reason it out though? If Q is too big, if Q is bigger than K, then Q needs to get smaller, doesn't it? How can this Q value become smaller?
Backward shift.
But why? Look at the expression for Q. If it needs to get smaller, then your numerator, the NOCl, would need to get smaller,
Bigger.
wouldn't it?
Never mind.
Your numerator would need to get smaller, so you need less NOCl. Well, that means you need less of the products in this reaction. And you need more denominator, a bigger denominator. So you need more NO and more Cl2. Well, those are on the left side of the equation. So I need more of the stuff on the left, and I need less of the stuff on the right. Then that's not a forward reaction, that's the reverse reaction. So when Q is bigger than Kc, we get a reverse shift. Okay. Now, do you guys get the basic logic of this? There's only 3 situations here. If I were you, I would memorize the last one, because in a later unit, that one's going to be important. If you memorize just that one, that when Q is bigger than Kc, it shifts backwards to reach equilibrium, then don't the others just sort of become obvious? Then when Q is less than Kc, we go forwards. And if Q is equal to Kc, you don't shift at all, that you're at equilibrium. Okay? So memorize that last situation. That's the most important one.